speaker is Arielle Blonder, who is an Israeli architect, based in Israel. Arielle is a graduate of Technical University in Haifa, and she's also a graduate of the MTech program in London. She has an office in Israel called Amalgam. Yeah, I'm practicing. And she's involved in different types of, she was also the founder of Fab Lab Israel. Yeah. Another point here, remember. What's interesting about Arielle's work is the kind of connection, and also in relation to our workshop, is kind of the connection between digital modeling, parametric design, and material behavior. And I think part of the lecture today will be also about this kind of realm of research and of material studies. So thank you, Arielle, for coming. And I think it will be quite an interesting resonance with the work we just saw from Rambo.
Thank you. So I thank you for the invitation, and I was very pleased and honored to be lecturing after an engineer. And it is as if I asked Gary to ask his question, but I didn't. His final question, because I think this connection might not have happened 20 years ago. We come from a culture where architecture was considered as something almost close to the arts, and fabrication was something to be done somewhere in the dirty world. It's a very clear separation, a clear-cut separation between design or the architect doing his thing, finishing the design, then moving it on to the engineer, and then from there to be sold by the manufacturer. And that's actually exactly what you were mentioning at the end of your talk. And I think it's much more fun now. We're fortunate to be in a world where we're doing iterative process, or at least where when it is positive and where it is constructive relationship between design, engineering, and manufacturing. As you were saying, we invite you to join us as early as possible, to be at the table, and to be part of this thing that I think goes around matter. I think one of the things that connects all of us together, design, engineering, and manufacturing, is this new look that we have on materiality. And since we are now preoccupied with matter much more than in the past, and I understood now that you are dealing with form finding. Some of you, I don't know if everybody who participated in the workshop or not. Some. Okay, so please forgive me if I'm saying things that are regarded for some. So this new occupation with materiality is what connects us. And our projects become more and more complex, and they are based on digital tools, these same digital tools that we use all along the chain. And this chain that is common for all of us allows us to sit at the same table and discuss and exchange ideas very early. And we see materiality in many forms. We see it in books, and we see it in material libraries, and we see it in diplomas that are centered on matter and materials at various levels. And along with that goes fabrication. I think never in the past have been architects or designers involved themselves in fabrication with their hands. And this is very exciting. So I've just collected 3 of the things I've collected in this very gallery, in the ZEZEZE, doing the list and collecting the cardboard and this, this was in London actually, in the canopy. But you see a bunch of, here it's MTech students in this case, building, fabricating, and this new connection to the material gives you some kind of responsibility and a different approach. So this is why a talk like that can be around material design and fabrication. And my material, my fascination, the one I'm going to talk about it today, is FRP, or fiber reinforced polymers, that we commonly call composites. I think this kind of leap or jump that we see towards from this abstract thinking to materiality and something very concrete, we can see it also, it's not coming alone. I think it's a parallel kind of paradigm shift that we see, a move that we see along these kind of 20 years, that where we see a move from straight to curvilinear, from abstract to material, and from a mechanical thinking to biological thinking. I'll go very quickly through these just to explain how it stands at the basis of my work or what I was researching. It seems like in the past years people have suddenly rediscovered the force of the shell. This surface active structure that conducts the loads to the ground over the surface and not through the material. It has been there all the time, obviously, since the planting in Rome or even before. Kind of forgotten for a few dozens of years, and rediscovered in a way. People are re-looking back at all these amazing concrete structures realized by Togofa and Candela and Isler and Otto and a few of the names I guess you were mentioning before. They are getting their kind of new bloom. We are looking back at these concrete shells, and we learn quite a lot. But we learn partially because of these guys. These guys have introduced the blob and the fold. You all know Gilles Deleuze with the Book of the Fall, and afterwards Greg Lynn, his embryological house, and actually introducing all these free-form structures that resemble quite a lot to these shells, but not really. And I think this difference between the free form and the pure shell gives you guys a lot of trouble. And sorry I missed the first part of the talk, but I can imagine that some of it was about that, about our tendency to do these kind of weird shapes, curvilinear, weird surfaces, and expect them to act in a way naturally as a surface. And it's not always with either metal or composites or glass, but also in concrete, just as we saw traditional shells. But this amazing concrete shell of Toyoito, Kakamigara, crematorium, had to go through a long process by structural engineer that did the morphogenesis of block structures. Sasaki, thank you very much. Mitsuo Sasaki. Had to go through a long process of morphogenesis to adapt the shell, which is not a pure shell, to be structurally viable. This leap, when we look back on these concrete shells, actually it makes us also look to Mother Nature that does these amazing shells quite in the same way, but maybe not exactly. We tend to see these shells as a pure form of structural form, but we can see that they are not either on primitive geometry or on a very simple ocular surface, and this raises some question. And this look, this new look onto biology is also a paradigm shift. I think is very important to understand where we are today and what essence, what is the meaning of our work. It means that we look back onto people like Ernst Haeckel, a biologist in the 19th century that was depicting these amazing radiolarias, and then we look at nature with these electron microscope images, and it goes back and it goes all the way to what we do today in 3D printing, full-scale 3D printing or object-side 3D printing of these same radiolarias. So we are kind of busy with understanding this biological world and what this could mean to us. We also look back on a theory level on growth and form, Darcy Thompson, which then brings with that new theories of evolutionary design and topology, genetic algorithm, etc., etc. On a very contemporary level, on a very material level, we have all the biomimicry, looking again onto biology and nature, trying to understand its principle, like it's done here. I think it's the most famous example of biomimicry adapted in materiality, the lotus effect and the butterfly wing effect that self-cleans itself, that cleans itself automatically, and then engineering all these materials that act in the same way on the molecular level, on the nano level, that clean themselves and are applied to surfaces as this material that is already commercialized. Or we can work with nature itself, with a molecule, with a tool of a biologist, with the thinking of a geologist, and instead of crafting and cutting and tooling, whatever we do, just grow it. And that's why I really like this project called Microtexture Field Cross. Because here, suddenly we don't need to adapt the material to whatever we want, it just grows. We will grow our furniture, we will grow our structure out of biological matter. I think this is probably the next paradigm shift that we are about to see in our world. And what excites me most about thinking about this is the fact that if we grow our materials, we probably won't need to put them in a mold. And I think that preoccupation with the mold and the role that the mold plays in our structure is huge. If we look back again on these amazing concrete shells of the last century, we can see kind of attempts to try and solve this problem of how the hell do you construct the mold, which is kind of another building, just to create the final building, which will be, for example, the concrete. So this pavilion of the Corbusier in 1958, I'll show you the final results. This is the final result. The mold was done by sand. Okay, putting it directly on the sand. And from this rather non-conventional solution, we can understand what the size of the problem they had to do these shapes in the mold to give it the final shape they want. Same goes for Nervi, that made a lot of effort to kind of develop his system of formwork. He was working mainly with concrete, develop a system of formwork to make it more efficient, to make it more viable. In that case, precast ferrocement mold that he was making, and modules that he could play around and twist, first to make it reusable, and second, to make it repetitive. Sorry. And this is the Gatti wool factory of Nervi, which is done with this ferrocement. Looking at, again, Toyo Ito's crematorium, contemporary, amazing structure out of concrete, a huge roof, a concrete roof. We see the effort, the tremendous effort put in the mold, and you ask yourself, what is the structure? Or what is the challenge? Is the challenge the concrete or the mold to make it happen? Moving to the other composite, actually, it has the same problem altogether. Composite materials of FRP are fibers and matrix. The fibers can be glass fibers, carbon fibers, kevlar, basalt, quartz, hemp, and many others. And the matrix usually is epoxy resin or polyester. Whatever the combination is, it has to be put in the mold, either wet layup or spraying or pre-preg. Pre-preg is material that is pre-impregnated with, the fibers are pre-impregnated with the epoxy and then manipulated, we'll see later. Infusion, whatever technique you would like to apply composite, you need a mold, either one-sided or double-sided, with or without vacuum, with or without autoclave. It's obvious that in some industries, this is not really a problem. In automotive, even in boat hulls, in furniture, or in wind turbines, these are very common usage of composites. This might not be a problem because you do a mold and then you can have it in a repetitive way for a series you usually produce. The problem comes with architecture. Architecture is one of a kind. Architecture today is differentiated. Architecture is non-repetitive. And architecture is very, very big. And then the problem of a mold gets really, really crucial. So then you ask yourself, if this material, this type of material, that is sometimes also referred to as a smart material, is it really smart to use it? Is it a smart material for us? Is it smart to use the composite materials for the architectural application when you know this is the cost of it? And the other comment I put to myself is it still a textile? Because these fibers, they should be operating like a textile. Now, if you've done some form finding experiment yourself, I don't know what kind of form finding you've done, but I guess you discovered that textile is a very, very small thing. So looking at Fry's auto work, maybe we should not look for a very smart material, but the wisdom of the material itself. Okay, so to know what does this material know, how does it operate, how does it reorganize itself, how does, in this example of cloth experimentation of Fry Auto, how does it self-organize, How does it get into a stable state? What does it mean, suspension from 3 points, from 4 points? How does gravitation actually affect the form that we get from these structures? And after Fayoto comes Heinz Hitzler with his application directly into shells, where he actually finds the shell of the shell by form finding. He hangs the fabric, hardens it, then invert it, just as Gaudi did with his hanging chain and the mirror underneath, and you get the exact form of the concrete shell. Optimized, obviously, because nature optimizes itself. Fabric, the fibers of the fabric are free to reorganize, self-organize into the most efficient form for suspension loads and then for compression loads when you invert it. So this is some of the outcome of amazing shells of Israel. Most of them realized in the 60s and 70s. Most of them still in very, very good condition. And you can notice that they're very, very thin compared to the span of the shell. And the reason they're very, very thin is that their shape has not been defined by an architect somewhere in his studio, but by nature in these models, in these hanging models. I like this diagram very much of Heinz Hitzler because actually he divides his shell not according to their form or according to their place or year, but according to the way they were form found. And he developed a few techniques for form finding, and actually he shows how little displacement, this is a monitoring of the displacement of the shell over 20 years. What little displacement you have when you do form finding of your shell and you don't invent it as is. So looking at that, I understand that this material, the textile, can naturally define the shape of a shell I would like to build. So it's a catenary shape. That's the form that the material would naturally organize itself. But then I'm asking myself, do I have any freedom? Or is this catenary used as it is, simple, pure, and I cannot intervene or I cannot articulate anything? And then I look back into nature, and I see these two shells, both of them performative. They perform, right? They don't break. One of them is very simple and very clean. That's the one that the engineers like. The one is rugged and has some pleats, and that's the one that engineers like a little bit less. Some of them because they don't understand, some of them because it contradicts the pure rules that they've learned, or because it's just impossible to compute. But it's very interesting to understand how these shells that are not in a clear surface operate, and that's kind of what intrigued me. So I start doing form finding experiments kind of in the way of Hitzler, by twisting it and changing it and interfering in the material. Fascinated by the way we can in cloth induce a huge three-dimensional change in a very small effort. And then thinking, can composite be shaped as textile? Can we look at fashion, for example, and see amazing three-dimensional structure, volume, and stiffness in some parts, induced in the textile just with simple operation, simple features. And again, looking at Easter, thinking if this is the material itself I'm manipulating, maybe it could be the structure itself I'm building by form finding. These are experiments that Isler did at the end of his career in his garden, spraying, he lives in Switzerland, so he can do that, spraying membranes with water in the winter, getting it to be shaped as actually form-found structure in full size. It just hardened into ice. So what's interesting in this kind of garden experiments in Whistler is suddenly you don't use form finding just to simulate the form or to find the form or optimize the form you'd like to find, but to be the actual thing. I'm sorry, now I see it's not working. So with these questions, actually, what I did in my thesis research, and that's what I'm talking to you today about, is try to do form generation by membrane self-organization, which is kind of simple. To induce complex double curvature from a lower energy manipulation taken from fashion design, to manipulate the boundary condition a little bit like our fellows architects building concrete shells in the 60s did, and I'm going to show an example of that. To integrate the formwork as part of my design process, and to use the form finding as a method for construction and not a method only for simulation. And the process is actually kind of simple. You hang a fabric. This is carbon fiber fabric, pre-preg, means that it's pre-impregnated with the resin in its manufacturing process. Pre-preg can be frozen for a few months. Once you take it out of the freezer, you have few weeks of workability when you use the material and it doesn't harden. And once you insert it into curing state, meaning you heat it in some way, it could be an oven, it could be an autoclave, which means the oven with pressure, then it gets into its final stage and it's stiff. So basically what you see is a huge experiment of form finding where just 2 or 3 layers of carbon fiber in this case hardened into the shape defined by what we call boundary condition, which is where you put the ropes, how you tie them. And that is the first proof of concept I did of working with a material. I can tell you that when I got to Gurut is the place where I did my experiments with the Isle of Wight in England. It's a multinational company that manufactures resins and fibers. And they have a huge prototyping workshop just by Aston Martin and Vestas, who are the 2 very natural clients for them, Aston Martin's the car and Vestas the wind turbines. And when they heard that I would like to do some stuff in composite without the mold, their reaction was, okay, you'll never succeed, but we have 3 days free because it was just between Christmas and New Year, so take the space, you can do whatever you want and we'll help you. They were kind of intrigued. And after a few hours, we had this proof of concept so we could go and move forward. Since we would like to integrate the formwork, which is actually the work itself, and form finding, I started with a digital form finding process. Now this was done in 2007. So by now I guess it would have been in Kangaroo and Grasshopper, which will be the next step of this research once it gets into PhD, which is its future. But this is form finding, prehistoric form finding, digital form finding, 3D Studio Max, cloth application, cloth simulation application. So first, get to know your tool, the digital tool. You understand that there is a set of definitions, kind of zeros and ones and percentages that of course have nothing to do with the actual material world. You don't put grams, you don't put the type of fibers you have in it because it's a simulation tool just for amateurs. So that was what I was working with. I was calibrating it with the material experience, doing crisscross with measuring physical experiments and form finding it. And then comes the step where I start to manipulate, a little bit like a fashion designer maybe, these form finding experiments and introducing what I call later features. In that case, for example, it's a stitch where you just put a rope into the fabric and then you pull it. It's a very simple operation that kind of changes everything, introduces millions of pleats, additional curvature, interest in the form, some augmented stability in places and weaknesses in others, and a big puzzling look that I got from Bureau Havel Engineering when I asked them to help me with that. When we look at these concrete shells, we see that all these traditional builders, they also had their kind of tricks to manipulate the boundary, because the weakest place of the shell, I hope I'm not saying too many odd things for an engineer. Please correct me if I'm saying nonsense, I'm just an architect. But I think you'll agree that the weakest place of the shell would be here. And then you have this trick that is the bit of folding back, okay? Folding to get it kind of extra stiffness, geometrical stiffness. And same goes for Nervi, that kind of undulates this Palazzo dello Sport and also divides its intersection. So what I did is very rough simulation, FEA simulation by ANSYS to see, you can see here the weakest point and how it changes tremendously or completely when you fold it up. And same goes with subdividing it and other features. So if I take these tricks of the old masterpieces of concrete and I add them to some tricks I get from friends from fashion engineering and fashion design, I took these 4 features to try and start to manipulate my shells. The pinch, opening and extension, stitches, and cutouts and seams. So this would be the digital model of the pinch. Literally, you just rise it up. This is the physical model of the same digital model. And the reference would be, in a way, the concentration of stresses that Nervi gets when he puts a column in the middle of this and directs the flow of stresses by these semi beam intervention in this ceiling. And then I started a very long series of digital form-finding experiments, some of them random, some of them are tested for some stability and further developed. There was no evolutionary algorithm done for this, but it could have been development in such research, where actually the only parameters you play is with the location of the stitches you put and the Z value. And you have infinite options for the creation of volume, for the creation of shape, and different types of stability. The second manipulation is the opening, the openings, and here you can see the digital model, physical model that goes with it, with a reference to Musmeci, an Italian structural engineer with this amazing bridge onto the Swan. So here is a set of form-finding experiment just to prove that, and the parameters here start to be more important. You have the geometry of the extension you put, the size of the orientation and the extension. It is weird because when you do the structural analysis of this, naturally you would say it weakens the whole thing because you just do a hole in this surface acting structure. But what happens when you do a buckling analysis, and in this shell the buckling is actually the most important thing to test. When you do a buckling analysis, you would see that it gains an overall stability. The displacement is huge on this little tongue or extension that we put, but the overall stability of the structure has improved. And that was interesting. The third feature I introduced was the stitch, and again the connection with the built reference and the physical model, and again a huge amount of testing. And the cutouts and opening, the digital model, physical model, and a recent, very recent example, kind of simulating biology, kind of simulating or just resonating these cutouts in the material. And here again, infinite ways that you could use it, either just for introduction of using light, or shaping the overall structure, or just reducing loads in places that you don't need them. So the process is very simple. Of the material according to the boundary condition, inversion, and then you get the form. So if you do the design of such a shell, you would do iteratively. Each time you change one of the conditions, either the place you hang the membrane or the height or the amount of stitches, the pull and the stitch, all these are parametrically controlled and would affect the final shape. Now here, ideally would come the engineer and do an analysis or a structural analysis as part of this operation, and we would continue the iterative process with the engineer. So how does it work? The process is just very simple. I cut the pre-prepped materials, I lay them up in a heated oven. The material comes in a size, in that case it was 1 meter 20. So if you'd like to build a large structure, you have to think about a way of how you connect it. Luckily enough, we could develop a way that we heat the oven a little bit. The material sticks to itself, no need for stitches or gluing or any accommodation between the layers. If you'd like to have a better connection between the layers, you need to vacuum it up. Usually you vacuum up the whole thing, the whole composite layup during curing itself. You can't do it when you want to formify, because then the force that would act on the material would not be gravitation, but would be the negative pressure of the vacuum. So you just vacuum the layers, then release the vacuum, but the layers are already sticking together because they've been heated a little bit. I forgot to mention layering, all kinds of corner details, I'll show it later, for reinforcement, and the tricks we take from sailing or from other boat building. Then we place what I call the features, the opening, the stitches, the pulling, all what we do to manipulate the natural hanging of the shell, the cuts, the ties. We tie it up, put there for curing. And curing is, it depends on the oven you have and the size of the piece and how you would like to ramp up, because you need to increase the temperature in a very steady way. Anyways, here it was very simple. It was just 70 degrees of curing, and after 5 hours this thing was ready. And 3 people can just invert the structure, which looks, I apologize, I mixed up the presentation. That's not the final one. 3 people can invert the structure that is 10 meters long and 2 meters wide, because that was the size of the wall. This is a mapping of the prototypes I did in this amazing week I was involved. How it evolved actually from one hypothesis to the other, developing this material fabrication system that I just explained. And this is the final outcome. It's not very beautiful, but its purpose was to test as many manipulations and challenges as possible in one structure. So you have the opening and you have the bending of the kind of leaf here. You have stitches on the other side. You have different ties on every corner. And that was actually the proof of concept of this very large structure made of 3 layers only complete materials. The layers are staggered and they are perpendicular to each other. These are the reinforcements. That's what they do when they do sails for boats. That's the way they reinforce it. And then that's why we put unidirectional composite, meaning it's not woven fabric, as we are working with for the membrane, the large membrane, but it's unidirectional, very efficient and very strong fibers that would act kind of as rods, reinforcement rods. Prototyping went on and on with all these openings and cutouts and testing what would be the limit of how many layers, how thin it could be, how thick it could be. And then came a part where I wanted to see how does this relate between the physical and the digital. I'm not an engineer, I don't have the knowledge of an engineer, and I didn't pretend to be. The only thing I wanted to know is if I'm in the right direction, meaning is my digital simulation coherent with what will happen in the physical world? That was first. And second, if I do this very quick analysis in Strand or in ANSYS and get some results, does it resemble in any way what would happen if I do physical testing on the physical structure? So this is the testing of the digital model versus the physical model. This is done in wet layup, meaning that it's not the pre-break, but you just cut the fiber and the matte fibers. You impregnate them with resin manually. And you can see there is quite a strong resemblance, even with these very simple tools. So when you assume that now we can take it into development to real simulation, form binding simulation according to the material properties of the fabric and the digital process, we can get very close to these shapes. So that was first. And second was the understanding, the structural understanding of what happens if we leave it this way, or we try to cover it with an additional layer, for example, foam, that would give it structural stability. So these are the digital simulation of buckling analysis, but just a membrane and then the membrane covered with foam. And what we did in the lab is frequency testing, because when you test a natural frequency of the structure, you get quite a strong prediction of the buckling behavior of the structure. And the buckling analysis the natural frequency analysis behaved quite in the same way as we expected it from the digital motivation. So we can imagine if we wanted to get really professional, some kind of nice engineer that would help me take the work onwards and cooperate, but it wasn't the right direction. And the same done with loading the material with loads and then measuring the displacement physically. So you can see the comparison between the unfoamed and the foamed material. It's not the same numbers, but the tendencies were always the same, okay, between the digital and the physical. And then I guess it means that it needs calibration. I'll finish with a very short case study because since I left the MTech, this work has been waiting for to be sort of saved by something. So it's going to happen with my PhD, but it happened also with this case study we call the Shaver. A group of people, Yasha was here before, he was part of the group. Guys just finished it now. Mushit and Zaharari, that was mechanical engineer, and Guy, mathematician. So we took this principle of construction of these shells, full-scale form finding by composite, and asking ourselves what could it be an advantage. And we thought of a place where we would like a repetitive structure but would be different in every in each and every place. And we thought about our beach. I hope that the international guys had the chance to go to the beach.
Yes.
Yes, you did. You saw the horrible shading structure we have there.
No.
No. Just plain shading structure made of wood. They have to be painted every year again because it's very salty and we don't really know in Israel how to treat wood to be on the beach. So that would be ideal to place to a material like composite where we could build shading structure. And also Tel Aviv, we have kind of a nickname of every beach. We have the beach of the dogs and the beach of the families and the beach of the couples and the beach. And configuration or seating configuration could be different in every beach. And that was the idea of this suggestion, that instead of doing one big shading element, we could do smaller shading elements adapted to the group of people we imagine would be sitting there. In addition, if you happen to be for a few hours at the beach using a shading element, if you're clear skin, fair skin like me, you need a shading structure, and you're looking that you're running around in shade. You're actually trying to chase a piece of shade because it moves around. So we try to think maybe we could devise a shape, find a shape that would perform in a way that the amount of people to find could stay in the shape all day. So we did this process, the process in MATLAB, where we define a cloud of points that we need to be, where we need the material to be. And in this cloud of points, we will have material, and this material will be then defined as composite and fabricate or form find in the way I showed before. So it was a cross between MATLAB and 3D Studio. Then we put it into CATIA in that case for the simulation. And then we realized that here, as we expected, there are not many loads or stress in the material, so we can even improve the performance by putting cuts, introducing cuts into the material. This is the latest simulation actually in Nastan that an engineer did for us, saying it is viable. We could see these kind of weird structures being around the beach, and I hope that in a year or two when you come again to Israel, maybe we can meet under one of those.
So again, I think we could have some questions, and probably some discussion. I mean, I think one of my kind of first question would be through your process. How does scaling up, starting from kind of physical modeling, very small scale, scaling up to a span of 10 meters, how would that behave differently? How would, if you expected it, or if it was kind of, what are the kind of knowledge that you gain through scaling up?
Do you mean in the prototyping process?
Yes, exactly.
It was not really a scaling up, because what I used to see as scaling up is doing my little, form finding tests, let's say in gypsum, and then trying to say, okay, this is going to be concrete 10 times bigger. And that's a problem of scaling up along with form finding, because the material behavior in scaling up is not the same. Where I did my experiments all the time with the same fabric, it was just extending it. It was not scaling up. Fiber stays the same. So, okay, maybe I increase the number of layers, I increase the grams of each, because you have a few thicknesses, okay, of the material, but it's not scaling up, it's not the concept of scaling up. And that's what is so amazing in this form-active mold, if you want, or doing the structure itself without any other tool, because you do it yourself with the same material you simulate, with the same material you do it. So I think the structural behavior was kind of the same for the big pieces and the smaller pieces. I didn't have these surprises. So the surprise will come up when we'll do a structure that is so big, for example, that you can't invert it. Okay? The structure has to be hanging and then inverted. That's the way it's formed. So then if we imagine a larger structure to be operated, if you want a structure of 10 meters high, so you won't have a crane flopping around a 10 meters high structure. So how do you do it? Now the problem is that subdividing does not exist in form finding. You probably realize it in your experiments. But once you change the boundary condition, if you subdivide, well, it behaves differently. So this is a challenge to be faced if we want to go big.
Did you try to use different materials except the fiber textile?
Actually, the beginning of all this was a competition, the canopy competition of the AA for the roof. And there were 2 finalists. And one of them was my structure, which was made out of cotton for the model. Cotton. Just cotton, textile. It behaves the same way. It was made out of cotton, and we did a model that was 1 to 2.5, I think, of the final canopy, because it was so easy. And at the end, it was together with Barath, and we were joint teams. It was a very good experience, actually, as a student. And we got to the finals, and then there were these 2 structures. So one of them was very complicated and intricate, with millions of parts and loads of work, and it was like 150 membranes, separate membranes, supposed to be calculated for shading the rain, but it never really worked. And the other one was ours. That was very simple. It was just 2 membranes. You hang them, you invert them. It was supposed to be uncomplicated. And at the end, the director of Barath said, "It's great, but I can't calculate it. I can't calculate it." So I don't know.
The regulation was 1.
And I can't calculate it, and it's supposed to be weakening the structure. And I was showing him, look, if I do this plain shell without, and then we had like 2 parts. One of them was with all these pleats, and the other one, this is much weaker than the other one. You know, try just to push it. He said, yes, but I understand what you're saying, but I can't compute it at the moment. And we were stressing time. So I think this gave me a lot of ambition to continue and you know, ask this weird question about interfering in the shell. But the beginning was with it should be operating the same. Actually, it's just that you don't have the amazing structural feature that you have in carbon fibers. That's what we're
I think to me this really opens up a new kind of topic about what exactly is form finding. I think from a structural sense, you know, when we do form finding, it's really about finding a form that distributes your load equally so that at each node it minimizes the force. And in automotive, for example, when they do form finding, it's about finding the least amount of drag, right? Mm-hmm. But also at the same time, when the automobile is hitting upon impact, that surface, instead of pulling in half, for example, it crumples. Mm-hmm. So that surface itself absorbs the energy of that impact before it gets to your body. And so there is this kind of optimization that the form is looking for. But I think in what you showed here in the last slide, for example, I think this is quite interesting to find a form that, you know, shades you for the maximum amount of time during the day. But I think when it comes to materiality, it's a bit difficult, right? Because when you talk about all these concrete shells, for example, a big part of that, how that works really is also the steel reinforcement. That's what's making it possible, not necessarily the concrete itself. You know, so to me, I don't know.
when we talk about material here, it's really difficult to kind of understand materiality and form finding in some ways. This is just my personal opinion, but I think it really opens up what is form finding, right, for architects, for engineers, for other design disciplines. It's just a comment.
No, I think it's a very important comment. I think that the notion of redundancy that designers and architects talk about more and more, they look at nature and they see that nature does things sometimes in a weird way, in a redundant way, or apparently redundant way. There's too much material in some places, and it's not as efficient as we think in some times. That is, if you look on one parameter, one kind of optimization towards one goal. For example, minimum amount of material, which is the usual goal that we'd like to when you do structural flow finding or optimization. But then you have the notion of multi-parameter optimization or multi-topic optimization. And sometimes you'll need to add some more material or add weaknesses in the structure in order to gain in some other places. So once you widen up your spectrum and you would like to get your architectural wish also through this form finding process, along with the optimized structural optimization, it gets more complex, that's for sure. And it will not be the minimal structure, because minimal structure is very clearly defined by the minimal amount of material, gravitation, that's it, point. But then if you'd like to evolve it, I think this would be the in between the Zah-Hadid form of I do whatever I want, you guys engineers solve it afterwards, I don't care about how it really operate structurally, how much material, how much effort we put into it, or I do the natural gravitation-only form of the shell. And I think this would be a suggestion of an in-between way, where you incorporate your designer's wish into this form-finding process and get it more complex, that's for sure.
Just two observations. One, I think the presentation is fantastic. I think it's quite interesting to see your work and dive into it. And it's also amazingly similar to some of the things that we were showing as well, which shows there's a lot going on in this field. But I suppose the observation was, as engineers, we have to look at the real world parameters, which you're designing for gravity loads, but actually in reality, we're looking at horizontal loads, non-uniform loads, etc. So until your last statement, I was going to jump in and say actually the minimum material might not be correct in what you say it is. Actually, it's the multi-objective optimization which takes into account different load cases, etc. So I suppose, I'm not sure what the question is, it's probably just an observation that it's something to look long and hard at, which isn't just gravity load, it's all sorts of parameters that go into play.
I think it's also a good way to celebrate. I mean, it's not necessarily the final solution, but it's a really good step. It's way better than just having a shape. Like,
but that's the interesting thing. Having done the Zaha job, you're right, you've just given this shape. And if it's the starting point for an investigation of what is the right form, and it could be subtly manipulating the starting shape, that's great. As an engineer, it's fantastic. If you're given that form and after making it work, that isn't a crowd. That isn't a
For architects, I think it's quite interesting because you suddenly deal with surface manipulation that you kind of opening into books and catalogs, starting kind of looking at good form finding through material studies, starting to see how shells really behave. So you can actually open up your own kind of virtuosity in these structures. I think that for architects usually you can press a button or you can see it,
how interesting because we don't start with preconceptions. We do an open mind as to what comes out.
Yeah.
And then the question is, at what point does aesthetic judgment jump in? Do you leave it out completely, or do you just trust what the computer tells you? I think there is a point when aesthetic judgment jumps in, absolutely.
I once had an interview, I don't remember what it was, doing evolutionary design. And supposedly everything goes by the algorithm. And then the same question, so when do you interfere and where does your aesthetic judgment come? And then she was saying, in this iterative process, when you comb your hair, it's an iterative process. At a certain point, it's okay. That's it. And that's the point where you stop combing your hair. And she was talking about evolutionary design. So I think, in a way, there comes a point where you interfere, and that's when you know that your care is competent, and that's okay. But if you're open enough to introduce from the morphogenesis, from the beginning of your forming, to form these natural processes, I think you'd be better off than just with your pen and paper on your own. Anyways, so it's kind of a dialogue.
I think one of the things we found with the private pavilion, which is kind of shaped in the same, using the same form planning techniques, is that even though they're really efficient in terms of the material is really thin, in the same way as this is really, really efficient, they're sometimes actually not that good spatially. So you get really, really tall buildings or really tall structures where you don't necessarily need them. So sometimes you think, if this roof wasn't so high, if you put it in plan, maybe it's about the same material, something like that. We had to kind of pull, on our first full plan shape, we didn't have that central column. So the whole structure was either really, really, really high, or it just chopped people's heads off, isn't it? But it's space. I mean, I think they look amazing, but if I had to critique the trial of pavilion in these kind of shapes as well, it's maybe spatially they're not that great. Which is kind of for you guys to worry about. But yeah, there's sometimes spaces where your head bumps into the edge or something.
I mean, I think the place where architects find, I think, an interesting niche is the kind of how you integrate these kind of structural ideas and structural engineering with other kind of sensibility. So, for example, currently taking a kind of quite a kind of serious engineered kind of system and trying to solve it, or trying to think, okay, by integrating more than one system, the structure, and say the infield, how can we work? And how do we be more responsive? How do we make it, not everything solves in form, or taking structure and putting it into fashion somehow. So pitching, surface manipulation that is really about, I think, different sensibilities a little bit, and bringing it back to the structure itself. So kind of balancing it and putting it, kind of layering ideas. I think that's where architects are kind of trying to find their voices. I think that's quite interesting.
One of the things we were talking about outside was about collaboration with different consultants. And I think what's slightly disappointing about some of this is you've got, I don't know if I'm talking rubbish or not, but you've got architects and structural engineers collaborating, I think, quite interestingly on these sort of ideas. But this one thing is you don't have environmental engineers and acoustic engineers actually collaborating in the same depth, as far as I'm aware. So, for example, why not do a form of a roof which was acoustically the perfect response to a particular form? You can end up with cane, actually, doing all sorts of stalactites and things. But isn't that just as a valid solution as a structural solution? I didn't really see that.
You do have some interesting collaboration with environmental engineers. For example, we had a project where through wind analysis you would be able to understand that you need a step, the way that you're stepping the building, or the way that you're developing a facade that kind of breaks the turbulence. Or for example, we had a forest full of bats, and that defined the level of your pit. So the wind comes, breaks in the facade and goes back just above the height of the trees. So you don't disturb these poor bats, because that's a protected animal in the Netherlands. So that's a little bit kind of, so you get an ecologist kind of coming and saying, no, I don't care about what your retail strategy is. You can't disturb fruit bats. And that's more
probably it's getting the behavior of fruit bats in.
That's more of a problem solving or a solution. Whereas when you're talking about this more in depth, when you use the logic of acoustics, for example, not to solve or to modify or to optimize a building, but to really generate it. And I think I agree with what you're saying. I had just experience with two acoustics engineers with a student that wanted to actually do a wall, a fabric wall according to acoustic principle. And he was saying, okay, so let's solve the problem once you have it. So maybe you get better acoustic engineering a little bit than as an academic, but I think I haven't seen any work that is not modifying or optimizing according to performance, but rather, because this you have a lot of.
No, but for example, if you're taking you know that PVC building, the one that works with the kind of the studio, the acoustics, that we discussed earlier. We collaborate with a company that was doing active sound reduction, so sound experience, and creating this kind of silent bubble. So that kind of works in now, technology goes now in Boeing seating and so on. And just by kind of introducing, kind of understanding the principle and bringing in technology, suddenly you think differently on how to define the kind of the wall section. And the wall section is actually then translated into a very different aesthetics. So I think in these points you can really kind of state or create a different statement about your project from the beginning. I'm going to do the minimum sectional, minimum width of a wall, and show how light it is just by discussing first with my acoustic engineer, not trying to optimize, but just trying to define it very differently. I think there are kind of interesting moments of collaboration. That's my take on it.
I'm curious to see what you guys are doing.
Yeah.
The form finding and the form you found actually at the end of your net. So send me this stuff.
Thank you very much.